In this video, we're going to talk about some tangent and chord theorems. So the first tangent theorem that we're going to look at is that if a tangent to a circle touches the circle at the radius or the diameter, it forms a right angle. And you can see that in the first image to the left. And this theorem is commonly used in Pythagorean theorem questions because a lot of times they'll give you right triangles and you'll have to find a missing side of the right triangle, but you'll have to know that there's a right angle because the tangent and the radius intersect, or the diameter. So just a reminder that this is a tangent line to a circle because it intersects the circle at just one point D. And this is a radius because it connects from the center of the circle to a point on the circle. So when a radius and a tangent intersect, they form a right angle. Same thing goes with a diameter. The second tangent theorem that we're going to look at in this video is if two tangents touch the circle from the same outside point, the segments are congruent to each other. So if you take a look at the image, tangent RS and RT both are drawn from the same outside point R to the same circle C. So they are congruent to each other. So anytime you see two tangents from the same outside point to the same circle, they are automatically congruent to each other. We're going to practice using these two theorems in some examples. I do recommend for each of the examples that we're going to see in this video that you pause the video, you try to think about it yourself, and then you unpause it to see if you got the correct answer and how to do it. Triangle ABC is circumscribed about circle O, and the sides of triangle ABC are tangent to the circle at points D, E, and F. If AB is 20, AE is 12, and CF is 15, what is the length of AC? So we're looking for the length of this entire segment AC, so I'm going to label that as X. So I see that tangents BE and BF are coming out of the same outside point, so that means they're congruent to each other. I see from this outside point, tangents AE and AD both come out of that outside point, so they're congruent to each other. Remember, two tangents drawn to the same circle from the same outside point are congruent. So if one of them is 12, then the other segment length is 12 as well. From this outside point C, we have DC and FC drawn, so those tangents are congruent to each other. So if one of them is 15, the other one is 15 as well. And that's all I need because now I have the two components of AC. I can just add the 12 and the 15. And I get 27 for the length of AC. In the figure below, quadrilateral TAEO is circumscribed about circle D. The midpoint of TA is R, so I'm going to pause a minute. R is the midpoint of TA, so I know that R splits TA into two equal parts. I'm going to mark that in the diagram. And then if I continue reading, they tell us that HO is congruent to PE. So here's HO, and here's PE. I'm going to put the same mark on them. If AP is 10, and EO is 12, what is the perimeter of quadrilateral TAEO? So I know this here, that we have tangents to the circle that come out of the same outside point. For example, let's start with outside point O. OH and OZ are both tangent to the circle, even though it doesn't explicitly say that in the question. OH intersects the circle at just one point H, and OZ intersects the circle at just one point Z, so those lines are both tangent to the circle. So that means they are congruent to each other. And for this outside point E, PE and ZE are both tangent to the circle from that outside point, so they're congruent to each other. So here, all four of those segments in pink are congruent to each other. So that tells me that each half must be 6. And that means each of these pieces has to be 6 as well. Now, I do see that we have out of outside point T, tangents TR and TH. So those segments are both congruent to each other. And out of outside point A, we have RA and PA that are both tangent to the circle from point A, so they're congruent to each other as well. So all 4 of those segments in black are congruent, so that means they all measure 10. And this is why marking the diagram is really important with the given information, because from our markings, we were able to draw these conclusions about which segments were congruent to each other. And now we have enough information to find the perimeter of the outer quadrilateral. This side is 16. This side is 20. And this side is 16. So all we have to do is 16 plus 16 plus 20 plus 12, the 4 sides. So we have 64 for the perimeter. In the diagram below of triangle PAO, AP is tangent to circle O at point A, OB is 7, BP is 18, and we're finding the length of AP. So I'm going to mark that as X, AP. Here, I have to recognize that OA is a radius of the circle. It connects the center of the circle O to a point on the circle A. And when a radius and a tangent line intersect, they form a right angle. So here's the radius. Here is the tangent line to the circle. So where they meet, we have a right angle. So what we have here is a right triangle. Also, keep in mind that all radii of the same circle are congruent. So OB is a radius of the circle, center to point on the circle, and its length is 7. But OA is also a radius of the circle from the center to another point on the circle, point A. And since all radii of a circle are congruent, if one radius was 7, the other one also has to be 7 as well. This gives us enough information to use the Pythagorean theorem because we have 2 sides of our right triangle. We have the 7, and then we have the 18 plus 7, which is 25. I'm going to write down Pythagorean theorem, which can be used anytime you have a right triangle and you have 2 sides to find the missing side. Just be careful, C is the hypotenuse, and you do have the hypotenuse here opposite from the right angle. So the 25 does need to get plugged in for C. The order for A and B doesn't matter. I'm just going to plug in 7 first and then the missing side X second. So we have 49 plus X squared equals to 225. From here, we can solve for the missing side. If I do 225 minus 49, I get 176. Oh, sorry about that. That's 15 times 15. We have 25 times 25. That should be 625. So if we subtract 49 from both sides, we have 576. And then if you take the square root of 576, you should get a whole number, and it should be 24. Let me write that over here. And I wrote x squared. You could have wrote b squared because I know in the Pythagorean theorem it's b squared. It doesn't matter. Let me put here that I took the square root of both sides so you can see what I did. And the missing side, which represents the length of AP, is 24. And that is our final answer here. In the diagram below, circles X and Y have 2 tangents drawn to them from external point T. Right away, I know that when we have 2 tangents from the same external point T, they are congruent. So tangent CT to circle X is congruent, and tangent ST to circle X are congruent. But wait, that's the tangents to circle X. We also have the tangent lines from point T to circle Y. AT is tangent to circle Y from point T. And ET is tangent to circle Y from point T. So those segments are congruent to each other as well. And that's going to be important that we mark that in our diagram. Anytime you have two tangents to the same circle from the same outside point, they are congruent to each other. If we continue reading, it tells us the ratio of TA to AC is 1 to 3. Anytime you have a ratio, you can represent it algebraically. I can represent the one part as 1x, or just x for short, and I can represent AC, or the 3 part of the ratio, as 3x. And it tells us that TS is 24. But if TS is 24, TC is also 24. So now we can set up an equation to find S that will allow us to find the length of SC, which is what we're looking for. I can make an equation that says 3x plus 1x, the two pieces of tangent CT, together must make 24. And if I solve real quickly, I get that x equals to 6. And then if I plug in, AT has a length of 6, and CA has a length of 18. And since AT and TE are both tangent to circle Y from point T and are congruent, this is also 6. So that means this also needs to be 18 to make 24. So SE, the length of SE is 24. Now we're going to take a look at some chord theorems. We're actually going to take a look at 4 of them and do some practice examples with them. The first one that we're going to take a look at is if two chords are parallel, so let's say AB and CD are parallel, the intercepted arcs, which means the arcs formed between them, are congruent. So in this example, if I was told that AB and CD were parallel line segments, the arcs between them, which would be arc AC and arc BD, would be congruent to each other. So they would have the same measurement as one another. If two chords are congruent, their intercepted arcs are congruent. So in the diagram, notice how chords AB and DC are congruent to each other. So then that means the arcs that each chord is touching will be congruent to each other. They will have the same measure. When a diameter is perpendicular to a chord, it bisects the chord. I want to point out that this also works with a radius. It's any segment passing through the center. So notice in the diagram, SQ is a diameter. And when it intersects chord, TR, it bisects it. It splits it in half. So when the diameter is perpendicular to a chord, notice the right angle. Not just intersects. Sorry if I misspoke. When it is perpendicular to a chord. So notice how the diameter and the chord intersect to form a right angle. That's why the chord is getting split in half. If there was no right angle there, if they were not perpendicular, then this would not be happening. So the diameter and the chord need to be perpendicular, and then that means the chord gets bisected. The other way around is also true. If you started off with knowing that you had a chord that was bisected and it intersected a diameter, then you would know that it's perpendicular to the diameter. This theorem is also commonly used with right triangles and Pythagorean theorem because a lot of the times they will give you triangles and you'll have to find missing sides and using this theorem. And finally, if two chords are congruent, then the chords are equidistant from the center. So let's say that chord AB and chord CD were congruent chords. Then we would be able to conclude that their distances from the center, so EG and FE, would be congruent to each other. We're going to practice applying some of those chord theorems to these examples. I would recommend that you try pausing the video and even going back to the chord theorems if you need to reference them, maybe writing them down somewhere, and then unpausing the video when you feel like you have an answer and are ready to check your work. Find the length of AB. So we're looking for segment AB. And segment AB is a chord. It doesn't go through the center. It's not a diameter. It's not a radius. AO is a radius, though. The 10 meters, that's a radius. So we're going to keep that in mind. So what I do know this is that the triangle that they give us is a right triangle, triangle AOC. Not only is a right triangle, but it also has a 60-degree angle. So that means that the last angle would have to be 30 degrees. So this is actually a 30, 60, 90 triangle. And remember, the ratio that the sides are in for a 30, 60, 90 triangle is 1 to radical 3 to 2. And they already give us the 10, which is opposite from the biggest angle, the 90-degree angle. So that's the 2 part of the ratio. That's the biggest side. First, let's get the 1 part of the ratio. So since the smallest and the biggest side are in a 1 to 2 ratio, we can just half the biggest side, and we get 5 for the smallest side. And the smallest side is across from the smallest angle, so across from the 30-degree angle. So the radius, OC, would be 5. And then we could find the length of AC. AC is the middle biggest side of the 30, 60, 90 triangle. So to get from the smallest to the middle biggest side, all we need to do is take the smallest side and multiply by radical 3. So 5 times radical 3 would be 5 radical 3. So 5 radical 3 is the length of segment AC. And notice how this segment over here is a radius of the circle. And notice how when it intersects the chord, it does intersect to form a 90-degree angle. It is perpendicular. And when a radius or diameter is perpendicular to a chord, it bisects the chord. So the chord is being split into 2 equal pieces. So that means that this half is also 5 radical 3. So then we can just put them together. 5 radical 3 plus 5 radical 3 is 10 radical 3. If we take a look at the next example, it says if AB, the segment, is 5x, and CD, the segment, is 3x plus 6, and these should have symbols here, find the length of AB and CD. And I'm just going to put those bar symbols on top, even though you don't need those to represent the length of line segments. That way we don't accidentally confuse them for the arcs. So I know this here, that we have 2 congruent arcs. Arc AB and arc CD. And we have a theorem that says congruent chords intercept congruent arcs. So the reverse is also true. If you have congruent arcs, they intercept congruent chords. They touch congruent chords. Arc CD is touching this chord over here. And arc AB is touching this chord over here. So those are going to be the congruent chords that are intercepting the congruent arcs. So all I have to do now is make an equation that says the 2 chords are equal to each other. And then once I find my x value, I can just simply plug back in. So AB would be 15 and CD would also be 15. And they should be the same because they are congruent to each other. Congruent chords intercept congruent arcs. In circle A, segment FG is 3x minus 4, and HJ is 14. Find the value of x. So what I see here is that chord FG and chord HG, chord FG and chord HJ are both the same distance away from the center of the circle A. Chord FG is 2 units from the center, and chord HJ is also 2 units from the center. So if 2 chords are equidistant, the same distance from the center, then that means that they're congruent to each other. So chord FG and HJ are congruent to each other. So once again, all I have to do is set the 2 chords equal to each other, and then I can just solve. And I found the value of x. In circle A, FG is 3, GA is 5, and AH is 4. Find PJ. So I'm just going to outline what we're finding. We're finding this chord, and LA. We're also finding this chord over here. The first thing I notice is that we do have a right triangle over here. And we do have the hypotenuse is 5 and the leg is 4. You could use the Pythagorean theorem, but it's also a Pythagorean triple, a 3, 4, 5 triangle. So that means that this will be 3 when you use the Pythagorean theorem. So what I notice here is that chord JP and LA are once again the same distance from the center of the circle. They're both 3 units from the center of the circle. And if chords are equidistant from the center of the circle, that means that they're congruent to each other. So that means they are going to be the same lengths as each other. Also, I do see the rest of these have to do with diameters and radii. I don't see any radii being perpendicular or anything like that. But since GA is a radius of the circle and GA is 5, PG is also a radius of the circle. So it's also 5. All radii of the same circle are congruent. So once again, we have a 3, 4, 5 triangle. You could use the Pythagorean theorem to verify. So FP would also be 4. And since LA and JP are going to end up being congruent, these pieces are congruent, and these pieces would be congruent. So we have 8 and 8, and that makes 16. So PJ would be 8, and LA would be 8 as well. Oh, we don't need to add them together, but each one separately, PJ would be 8, and LA would be 8 as well. Moving along to the next one. Circle O has a radius of 5. So I already see that OD is a radius, and it's filled in as 5, as is OA. But also CO is a radius. We already have the 2 part, so that means that needs to be 3 to make 5. And I also see that BO is a radius, so that's also 5. I just want to fill in as many as I can because all radii of the same circle are congruent. And CE is 2. Diameter AC is perpendicular to chord BD at point E. And when the diameter is perpendicular to a chord, it bisects that chord. So this chord is getting bisected or split equally in half. And just like in the last example, you could use Pythagorean theorem to find the last side of the right triangle. But the hypotenuse is once again 5, and one of the legs is 3, so it's the same as we had in the last example, where the other leg will be 4. But once again, you can use Pythagorean theorem in order to verify if you wanted to check that out. And there we have it. The length of BD is 4 plus 4, which is 8. That one was super straightforward there. Okay, this will be our last one for this video. We have circle O shown below. Chords AB and CD and radius OA are drawn such that AB is congruent to CD. I'm going to mark that. So chord AB is congruent to chord CD. And if I have congruent chords, I already know a couple of things. I do know that they intercept congruent arcs, so these arcs would be congruent, but I think this question is about segment lengths, not arcs. I also know that if chords are congruent, they're equidistant from the center. So EO is going to be congruent to OF because they're going to be the same distance from the center of the circle. They also tell us that OE is perpendicular to AB and OF is perpendicular to CD. We know that OF is 16. Oh, and that means OE would be 16 as well. We know that CF is Y plus 10. And CD is 4y minus 20. Determine the length of DF. And then determine the length of OA. So first we're finding DF, and then we're finding OA. So since the chords are congruent, on this chord, we would also have y plus 10, and the whole chord would once again be 4y minus 20. So when we find DF, whatever we find for DF, and let me just use a different marking than I used for the other segments, it's going to be the same for AE because they need to total to the same amount. So what we can do here is we can say, okay, if FC is y plus 10, so is this. And if EB is y plus 10, so is this. And then I'm going to make an equation that says if we do y plus 10 plus y plus 10, we get the total, which is 4y minus 20. Combining like terms, we have 2y plus 20 equals to 4y minus 20. If I subtract 20 from both sides, and I subtract 4y, I have negative 2y equals to negative 40. And then if I divide both sides by negative 2, I have y is equal to 20. So the y value here is 20. And now we can find the length of DF. I can plug in for y plus 10, which is 20 plus 10, which is 30. So DF is 30. And then let me put that in here. So AE is also 30 if DF is 30. And now we need to find the length of OA, which we can do using the Pythagorean theorem, because we now have two sides of the right triangle. We have the 30 and the 16, and we just need to find the hypotenuse. So we can do 16 squared plus 30 squared equals to c squared. A squared plus b squared equals to c squared. 16 squared is 256. $30 squared is 900. And if we add them together, we get 1,156 is equal to c squared. You can put that into your calculator, the square root of 1,156, and it works out to a nice number. It works out to 34 if you take the square root of both sides. So we have that OA is 34.